This question is about Rutherford scattering experiment in which when the alpha particles are thrown at a certain value of kinetic energy E0, those are deviated from their straight path due to the electrostatic force of repulsion from the nucleus of the gold. So, but what happens when these alpha particles are thrown at an energy greater than this value? The fraction of alpha particles are scattered at an angle close to 180. So, why is this abnormality? Why is this special observation observed by that scientist? We will understand with the help of first understanding the what is a Rutherford experiment is all about. So, let me show you. So, for example, this is a gold nucleus, have a positive charge, and we are throwing an alpha particle, which is two protons and two neutrons. So when you will throw it with energy E0, a kinetic energy of E0, so what happens? It deviates from it. Okay, and all the alpha particles deviate at a larger angle, but not enough close to 180. What happens when you throw with energy greater than E0? Something special happens. Okay, now you have to understand when you throw with energy E0, this loss of kinetic energy converts into the gain in electric potential energy only at that limit when this proton or this alpha particle or this charge does not enter in the periphery, in the boundary of alpha particle, right? You see that it has went very close, but it is deviated, right? But when we throw it with an energy more than E0, so students, let's say now we throw it energy greater than E0. Now it hurled towards this and it reaches the boundary. And when it enters inside it, so what happens? This is a gold nucleus having a radius R. And you know that the universe's strongest force is a strong nuclear force. Now this force will interact with this one. And what is the limit of this force? This force, strong nuclear force, is capable to combine the nucleons within this range 10 to the power negative 15 meter. So if you are throwing it with this energy more than E0, then it reaches to that point where then strong nuclear force interacts with it, not the electrostatic force of repulsion. So from here, it is, you see that it is bounced back at an angle very close to 180, right? So it only happens when the strong nuclear force interacts. So why this deviation occurs? I hope you get your answer when it interacts with the strong nuclear force. Okay, students. So this is what Mach scheme says about it. Okay. Now, how can you utilize this value of energy to find the estimate nuclear radius of gold? Okay, now we will understand it with the help of law of conservation of energy, right? So just imagine when you are throwing this alpha particle with the energy E0. For example, students, when thrown at energy E0, how the energy conservation is obeyed. You know that at this point, the energy is in the form of kinetic energy E0, right? Okay. So where it will go with this energy, it will go to the closest to the nucleus. You can imagine just the like close to the boundary of nucleus. At this point where it will stop, so all of its kinetic energy is converted into the electric potential energy, and you know that that electric potential energy is equals to the work done. Work done is equals to the gain in electric potential energy, and that is k q small q divided by r. So this energy has been converted into the this form, right? So right now this r is a radius of the closest approach, right? So this radius, so from with the help of this we can find out the k q small q over r. The small q is a charge of alpha particle, q is a charge of gold nucleus, r is a distance of closest approach, and E0 is the kinetic energy. So this is a law of conservation of energy. With the help of this you can find the estimated radius of gold. Okay, now the next question is gold 198 AU 198. is radioactive nuclide of gold, and it decays into the stable mercury Hg198 with an emission of beta particle, followed by, which means that along with the beta particle, one or two gamma photons are also emitted, which you know that gamma photon is only emitted from an excited nucleus, right? So even after the emission of beta particle, still the nucleus of gold is excited. Nucleus of mercury is excited. So how it released that energy in the form of gamma photon. And in the first question, we have to find out the decay constant of gold. So we can find out the decay constant, lambda times half life is equals to natural log of 2, right? So you can find out the decay constant if you divide the half life. Okay, and the half life is 2.69 days, which you should convert it into the seconds. So natural log of 2 is 0.693 divided by 2.69 times 24 hours, and in 1 hour we have 3600 seconds. So that will be our decay constant. So this is 2.98 times 10 to the power negative 6 second raised to the power negative 1 per second. So this is the decay constant value. So the next question is, a sample contains 5 milligram of pure gold. Determine the mass of HD. Now we can consider the Au198 as a parent element, radioactive element, which is decaying into the mercury, right? So with the passage of time, the mercury quantity will increase and its quantity will decline. All right. So how much will present after 1 week, right? So we know the half life, 2.69 days. We know the initial quantity of the gold, and you have to find out the mass. Now we have the two methods for SL and HL, right? So I will tell you the alternative method for HL students later. Let's go through the SL method first. Okay. So we know that, you know that if we find the number of half lives which were passed, which were spent in a 1 week, with the help of those number of half lives, because we know after every one half life, the amount of this substance will reduce to one half, right? So how can we find the number of half lives? So for this, we know the total time, that is 1 week, 7 days, divided by 2.69 days. So number of half lives is, and its answer is 2.60 half lives. Okay. Now we want to find out the mass of Hg, right? So why not we first find that how much mass of the gold will remain behind? Means that we want to find out the mass of undecayed, right? So mass of undecayed gold Au198 that will be left behind. We can apply this formula, a general formula, with which tells us how it varies. So 1 over 2 raised to power half lives, number of half lives is n multiplied by the total mass in the beginning, right? So it should be 1 over 2 raised to power 2.69 times 5 milligram. Okay, and that should be, so I calculated it is 0.82 milligram. Just this mass of the gold is left behind, which means all the rest of the mass has been already converted into the mercury. So that should be the mass of decayed, right? Okay, or the mass of, we can say, mercury. Mass of mercury 198 should be 5 milligrams is minus 0.82 milligram, right? So that should be, so dear students, it is approximately 4.2 milligram. Okay, now we are heading to the next method that is only specifically for HL students. Okay, if we draw the graph right now, let's say, okay, because you know that the mass of the mercury will decrease proportionally, right? The mass of mercury will follow this curve. Okay, and you know very well that the equation for this is m is equals to m0 e raised to power negative lambda, and this t is a time that is given 7 days. Okay, and so right now it is the 5 milligram. Okay, what about, this is the, sorry, this is the gold. If I said mercury, that was mistaken. Okay, so what about the mercury? Mercury's amount will increase like this. Okay, so what, how to find out the mass of gold that will be left behind? So that is 5 milligrams. Okay, or you can say 0.005 e raised to power negative the value of lambda, right, which was 2.98. 2.98 times 10 to the power negative 6 times 7 days. 7 multiplied by 24 times 3600 seconds. Okay, this will give us the mass of gold that will remain after 7 days. And you know it already, we had already calculated it here. It was 0.82 milligram. So 0.82 milligram. So what will be the mass of mercury? That should be 5 milligram minus, once again the same thing, right? So 4.2 milligram. Okay, so it means that it is almost 4.2 milligram. Where, by the way, it is located, it is it not very close to this point, right? So this is a mass of mercury, and then it means that this is 7 days. Okay, and if this is a mass of mercury which is 4.2 milligram, then this should be the mass of gold which is 0.82 milligram. So I hope you understand this graph. So students, now this question is about the gamma decay, right? You remember we discussed in the start that when the gold converts into the mercury, it emits the one or the two gamma photons depending on that how much mercury nucleus is unstable in terms of its energy. Okay, now, when the gamma decay happens, these are the frequencies of the gamma. Okay, the, I mean, one or two gammas are photons. Photons are released, so those two, one or two gamma photons may have one of these three frequency. Okay, now we have to understand and we have to explain how this observation provides evidence that nuclear energy levels are discrete. Now you know that when electron jumps from one l- energy state to the another energy state, okay, it absorbs the energy, it absorbs a certain amount of energy, and then when they de-excite, it releases the same amount of energy, but that was for the electron. What happens for a nucleus, right? So nucleus also release a certain amount of energy. Why I am saying it? Because if I consider this frequency, which is 1 multiplied by 10 to the power 20 hertz, so it corresponds to the one single wavelength. Okay, one single wavelength of the gamma. All right, so if you can find out that wavelength, so that wavelength can be equals to c over f. You can find that wavelength. Okay, that wavelength will represent the wavelength of photon when a nucleus of mercury jumped from the one energy level to the another energy level. I think it is better if I show you first the equation, right? So au 79 180, it is just for understanding, you don't need to mention it even. So they said in a question that it released the beta particle beta negative, so it converts into hd. You know, the number of protons increased by 1 and nucleon number does not change, plus this is a beta particle and this is an anti neutrino and this is a gamma photon. Right now I'm just showing you the one, and this is the wavelength of this, sorry, the frequency of this gamma. Okay, they may release the two photons also. So if we show this thing in the terms of energy level, right? So this release the beta particle, right? Beta negative particle, and it converts into the mercury 8180. Now I'm writing here the Stark sign, which shows us that it is the unstable nucleus, right? So what happens, dear students? Here, this is a beta okay, and some energy is released. We can find that energy, but that there's a no need to find that energy right now. Okay, so what happens at this point? It jumps to another energy level, right? So if it is releasing one gamma, just one gamma, then this mercury nucleus will be finally in a stable state, right? It will be in a neutral state. But during this transition from the one energy level to the another energy level, a gamma photon is released. And what is the energy of that gamma photon according to the Planck's equation? That is E is equals to hf, right? Now remember that this f is a c over lambda, so hc over lambda. But what about this E, dear students? This E is the difference of these two energy levels. Okay, this E is the difference of two energy levels, right? Now, this quantized amount of energy and quantized amount of frequency and wavelength is in itself evidence of the energy levels of nucleus. So discrete means one value of wavelength, one value of frequency, and also for the energy. So finally, E is equals to HF. Observed gamma photon have a fixed discrete energies, right? And this gamma energy equals the difference between the nuclear energy levels, just like I have shown you here, right? And then the gamma photons are emitted when the nucleus undergoes transition between its energy levels. So I have explained you all of these points with the help of equation, diagram, and the Planck's equation. I hope you understand this solution.